Okay, so we basically have been talking about current sources, and the last time we saw this configuration, this is my general current source, right? And to bias the first one, I did this, and to bias the next one, I had the same amount of current but a much smaller device, right? And it was about 1/4 smaller or something like that, right? So the width was about 1/4 of the others. The current was the same. Alternatively, you could reduce the size of the current also. Yeah. Now, so you would have to make the current 4 times. Okay. The obvious problem with all this was that I am burning too much current. So I'll need one reference current source, and from that reference I'll create these two. Right? There's no other way. Now, is there a better way of doing things? Now, remember, all we are trying to do is as follows. And where is Bharat? Bharat is missing. Okay, so what Bharat had pointed out a long time back was that the gate of the bottom device should be at Vt plus VOV, and the gate of the top device should be at Vt plus 2 VOV. Okay, these are the two potentials that I have to create. Right? This is what we want to start with. Now, what if I do this? Okay. If I do this, then let's number the transistors: M1, M2, M3, M4. Now consider this first. Okay, consider M1. The gate of M1. First of all, M1 is conducting a current which is equal to I. Okay, this is not complete, I think. So don't worry about the details. Follow my argument. M1 is conducting a current of I. So what do you think is going to be the gate voltage of M1? Louder? Vt plus VOV. So what I have written in red is correct. So this is done. Okay. Now if I draw it this way, if my topology is like this, then automatically the drain of M2 is at Vt plus VOV. It's forced to be at Vt plus VOV. Okay? The drain of M2 is forced to be at Vt plus VOV. Now, if I need Vt plus 2 VOV at the gate of M4, at the gate of M4, I need Vt plus 2 VOV. This is what I need. I don't yet know if I have it. Okay, this is what I want. So suppose I want Vt plus 2 VOV at the gate of M4. Then what do you think is going to be the voltage at the source of M2? VOV. Is that enough to keep M1 in saturation? Yes. Is it enough to keep M2 in saturation? Assuming Vt is larger than VOV, which is usually the case. Okay? This is usually true. But as long as this is true, this works. Right? Now, the assumption here was that the gate of M4 and M2 is at Vt plus 2 VOV, which is a very strange assumption because right now the gate of M2 and M4 gates are hanging. They are not connected to anything. Right? So it's a very, very strange assumption. If something is not connected to anything, you can say nothing about it. Okay, so there is nothing that determines the voltage at M2 and M4, gates of M2 and M4. So what we could do is as follows. First of all, we know that the potential at the drain of M2 is Vt plus VOV. Right? It's marked with blue. That is for certain. And I plan to push a current I through this. Okay? What if I just put a resistor over there where I've drawn it, and I make it of a value of VOV by I. Suppose I cook up these values. Okay. Suppose I create a resistor of this value over there. Then what can you say about the potential at the other end of the resistor? 2 VOV, which is exactly what you wanted. For certain. Right? Now all you have to do is hook it up. And you've got what you want. Yes, question. So you are saying that let's delete M2 altogether. Vt by I. Vt by I, right? Not VOV by I. No, but that won't work. This you want the drain of M1 to be at VOV. Why do you want it to be at VOV? So I need a resistor of Vt by I over here. Agreed? So you are saying let's do this. No, this is fine, right? No, now it is correct. It's correct, right? Now, fine. So this works. But there is a slight problem. I did not do this to start with. Why do you think I did not do this? This is wonderful. Your name is Akhil. Wonderful. So this could be done. But we don't do this. Why not? What do you think is the voltage at the drain of NP? Look and tell me. Drain of M3. Most certainly it is VOB. So, on one side I have M1, the drain, gate and source are at voltages of DC plus VOB, DC plus VOB and 0 respectively. On the other side I have M3, drain, gate and source are at voltages of VOB, DC plus VOB and ground respectively. Do you think the current on M1 will be equal to the current on M3? Remember, the current through M3 is a strong function of VGS, fine, but it is also a weak function of VDS. So the currents are not going to be identical. They are not identical. They are close to each other, but not exactly equal. However, if I have what I drew before, now let's look at the drain, gate and source of M1. The drain, gate and source of M1 are at what voltage? What's the drain of M1? VOB. So the drain of M1 is at VOB, gate is at VT plus VOB, source is at ground. Drain, gate and source of M3 are also at exactly the same voltages. So the current through M1 is going to be precisely equal to the current through M3. Okay? This is the reason why we prefer this. Fine? Yes. Now there is no margin. We don't want to have any margin. We want to be over there. We want to be at the just at the edge, because that will maximize the range of voltages at the output. Yes, question. Okay. So Nallam says that why, okay, if this is what you want, why don't we do this? Vt by I. Right? This is your question. This is okay. Only problem here is that Vt is, what is the value of Vt? Huh? 0.65. Where are you coming up to these numbers? What I wanted to say is that the value of Vt changes with temperature, from technology to technology, from device to device. Even if you change the length of the value of Vt is different. Okay? So basically Vt is something which is very, very unpredictable. You shouldn't build resistors based on Vt. Okay? The value of VOB in any case is something which you can kind of choose. Okay? If you say that I am going to keep VOB as 200 millivolts, it's yours to play with. Right? You can also have a little bit of margin on VOB. You can say that, okay, I don't want 200 millivolts, I'll keep a little bit of margin, I'll make it 250 instead. That's also possible. Right? Whereas VT is something very, very unpredictable. You can't deal with it. So this is why this is not done. If you can do something with a transistor, with a MOSFET, then you do it with the MOSFET. If you really can't help it, then you start using resistors and so on and so forth. Alright? So it can be done with a MOSFET, just stick to the MOSFET. Is this okay? So what have I achieved here? First of all, I have achieved the precise mirroring, which you have seen. I have explained already. Number two, I have achieved a huge amount of power savings. Instead of the 3 current sources, I have boiled it down to 1. What's the bad news? The resistor is the bad news. Okay. We don't particularly enjoy using resistors. You get something with this. Right? So there are various other kinds of current mirroring techniques which I'm not going to discuss. There are ways to get rid of the resistor over there also. Okay. Yeah, we can do a lot of different things, don't worry. So that's what I'm saying. This is not the last word. There are a lot of more designs available in different textbooks. So we might want to look at some of them, right? But this is where we are going to stop. Now, all of these are basically biasing strategies. Okay, so in this course, this is an important topic, but it is underplayed. So over the semester, you will find that I'm going to be using, I'm going to be assuming that you know how to bias MOSFETs. You know how to bias devices. Okay? It takes a little time to understand how to bias different MOSFETs, but the crux of it is this and what we have talked about before this. Okay? So these are different techniques used to bias MOSFETs. We won't be talking about all this very much, but be aware of it. Now, when you are biasing devices, you have to make sure that things don't change when you change temperature. When the temperature on the chip changes, things should not jump here and there. Everything should remain stable. So all of those things have to be considered one at a time. I'm not going to talk about them right now, and I'm warning you that this entire topic is going to be underplayed. I won't be able to put as much attention to it as it deserves, unfortunately. Okay? It's a huge topic. Biasing is a huge, huge topic. This is the meat of it. I won't be able to talk about it in much more detail in the course. Hopefully, I'll be able to give you some more hints here and there. But you might have to, not you might have to, you should look at a couple of books and see what is traditionally done. Okay? Yeah. Bad news because of the resistor is first because you need an additional mask. An additional mask increases costs, reduces yield, and is bad news in general. The boss won't be happy that you need a resistor. The other bad news over here is that you need a specific value, which is VOV by I. And we hate talking about specific values. Okay? If you try to make a specific value, the tolerance of it is something like 20%. So you have to build in that margin onto that resistor. You have to make sure that you accommodate for that 20% here and there. Variations. That's basically the balance. Not this one. This would be, no, this would be made with polysilicon some material, not with the MOSFET. Area will also be high, depending on the value of the resistor. To start with? Good question. We'll have to talk about it later. We usually don't make a reference current source. We start with a reference voltage source. It's called a band gap voltage reference. We'll talk about it at the fag end of this course. That's why I'm saying that this whole topic is going to be underplayed. Okay, we'll be able to talk about band gap voltage references only at the end of this course. So we need a band gap voltage reference, and from there we are going to generate a reference current. Usually we don't build temperature invariant current sources. We don't build. We do build temperature invariant voltage sources. But with temperature, we would like the current to adjust itself so that the MOSFETs still behave the way we want them to behave. Okay? So that reference current source is not really a reference. It's a current source. It's not of exactly precisely this value. The value we want. Does that answer your question, kind of? It doesn't, I know. We won't make a reference current source to start with. We'll make a reference voltage source, a band gap voltage reference source, and from there we generate the current source. Later on we'll do this. We need an Opamp to do it. So I have discussed the Opamp. Yeah. This is M2, yes. It's in saturation as long as Vt is more than VOV, which I have pointed out in brackets. Hopefully it is. Usually Vt will be more than VOV. Usually Vt will be 0.3 volts, 0.4 volts, 0.5 volts, 0.6 volts, something like that. VOV will be 0.2 volts is a very good number. 150 millivolts, 200 millivolts is really, really good. You don't want your VOV to be more than that. Yeah? Okay, so I'm going to close this topic, and now we are going to start talking about how to use the MOSFET as an amplifier. Now, I'm sure you have all done this with bipolar junction devices before. You have done common base, common collector, common emitter, amplifiers, etc., etc. So I'll quickly rush through the same thing with MOSFET. Okay? So the first one is the common source. Why is this called a common source? Okay, so first of all, my biases are in capital letters, the signals are in small letters. So capital VGS is the bias voltage that I apply across gate and source. How do you create this bias voltage? Huh? No. From the previous discussions. Look, notice I've got an ID over there. Huh? So this is going to be what is unsaid, but I'm going to say it once at least. It's a little complicated here. Something like this. Okay, so you apply any voltage at the gate of the bottommost device. It creates a current through this. Okay, and that current is reflected through this. Same size. Let's say everything is of the same size. All right. So this is a very crude way of doing things, but this is an example of how it could have been done. In future, I'm not going to draw this, unfortunately. That's why I'm again saying I'm going to underplay this. So by hook or by crook, you make VGS, capital VGS, such that the MOSFET conducts a current ID. Okay? With a reasonable value at the drain voltage. You have to do this. This is your business. Now once you do this, you apply a small signal at the gate, which is V in, and you are interested in measuring the small signal that comes at the drain of the device. Okay, so at the drain of the device, you will see a DC large voltage, which is something like VOV plus VBS, some VBS you are going to see. On top of it, you are going to see a small signal superimposed, which is the output of the amplifier. Right? This is the plan. Now, the question to you is, what is the relationship between V in and V out? Yes? Okay, everyone has the answer, but how do you do this? How do you attack this problem? You are going to replace the MOSFET by its small signal equivalent circuit, number one. You are going to null all the voltage and current sources. When you null a voltage source, you make the voltage source 0 volts, which means you make it a short. When you null a current source, you make the current source 0 amperes, which means you throw it out and make it an open circuit. So you null the current source and you null the voltage source and you replace the MOSFET with its small signal equivalent circuit, and the small signal equivalent circuit, the simplest small signal equivalent circuit is like this. Okay, the value of the control current source is GM times VGS, and VGS in this case is equal to Vin. So you can forget about everything else, and in that case the voltage at the output is going to be how much? Okay, the gain of the amplifier is V out by V in. So I'm going to call that AV, that's the gain of the amplifier, is equal to V out by V in, which is equal to minus GM times RDS. And what do you think this value could be? Something like 20, minus 20. Okay, it won't be more than that. It won't be minus 40. It could be minus 10. Minus 20 if you have made a video of these, don't. Alright. If you talk about bipolar junction devices, a simple common emitter amplifier could give you a gain up to even 100. Okay, with the MOSFET, this is very, very limited. You have to live with something like 20. Now, what if I start talking about capacitors? I didn't talk about capacitors, right? But the MOSFET has capacitances also. So let's, shall we take a look? So what are the different capacitors? Gate to drain, then gate to source. Is the gate to source capacitance relevant at all? You have a voltage source in parallel with a capacitor. There is no effect. Okay, so this is not relevant. What else is there? What else do we have? Body, drain to body. Let's say body is at a constant voltage, which means that the body is at signal ground. So drain to body will be drain to ground. Anything else? Yes? Nothing else? There is one more. Source to body? Source to body, at least let's talk about it. So both sides of this capacitor are at ground. Both the sides are at ground, so therefore it has no effect, no role to play over here. We are missing out one, gate to body. Does it matter? That's first of all, that's only in very weak inversion, and secondly, even had it been there, will it matter? Body is at signal ground, so it's exactly like CGX. So it does not matter, even under weak inversion in all circumstances, it does not matter. So this is basically all we have. I'm going to delete the ones that I don't need. Okay. And now, what do you think is going to happen? So I'm going to treat the capacitances as impedances. Each of these impedances have value of 1 by S times the capacitance, or 1 by j omega times the capacitance. Right? And then I'll have to do an analysis. Agreed? So shall we quickly try to do that? First of all, the drain to body capacitance, it comes in parallel with RDS. So can I lump them together? I can lump them together. I'm going to call it as Z drain is equal to and I'm going to lump them together. Now what do we do? Kirchhoff's law. So is this okay? I have basically done a Kirchhoff's law at the output node. The sum of the three currents going in three different directions is equal to 0, and then I've put 1 on the other side, and then you have to put all the V outs together, all the V ins together, and you have to rearrange the equation. That's okay? Yeah, minus. I put it minus outside. No. Let's go back 1 second. This is what it was. This is correct. And now I'm going to take V out common on one side and V in common on the other side, and therefore I'm going to have V out by V in something like this. Okay, and then of course ZT you have to expand that with whatever you have. Alright, so it's basically straightforward. There is a little bit of manipulation, algebraic manipulation that you have to do, right? And it looks like there are no shortcuts, but believe me, there are shortcuts. Now, first of all, yes. It is actually V out by Vgs. In this case, Vgs is equal to V in. Depends on what we ask you for, right? And if you are asked to find out V out by V in, you find out V out by V in. Mostly that's what we ask, V out by V in. Okay, now first of all, what do you observe here? Are there poles and zeros? How many poles are there and how many zeros are there? There is a right hand side 0, fantastic, and pole, left hand side, is there one pole, two poles? There is one pole. Check. There is one pole and one zero. 1 by this should be there. there is one pole. Just check that there is exactly one pole. ZD, 1 by ZD is going to be equal to 1 plus SCDB RDS by RDS. So, alright, so what I'm going to do is stop here, give you a 5-minute break, and we are going to come back. Thanks.